Here are solutions to the final exam for ECE 376 for fall 2023. The first problem looks at hardware. Come up with a circuit to output a binary 0 volts, 5 volts. So what I want is when the resistance is 4,000 ohms, I get 0 volts, 5,000 ohms, or 3,500 ohms, I get 5 volts. So at 3,500 ohms, I output 5 volts, and 4,000 output 0 volts. So that gives you that little Z pattern or hysteresis. That's a Schmidt trigger. So that's the form of the Schmidt trigger. To design it, I need to figure out the voltages. Using a voltage divider, I convert the resistance to a voltage. I get 4 volts when the output turns off, 3.889 volts where it turns on. What that tells me, the on voltage is less than the off voltage, so connect to the minus input. The on voltage is 3.889 volts, that's your offset. And the gain, that's the slope. The output changes by 5 volts as the input changes by 0.11 volts, gives you a gain of 45. So I need a slope of 45 to 1. Pick something large like 450K, 10K, so that the loading on your voltage divider isn't too large. On to problem number 2. If I have a light sensor where the resistance versus light level varies like so, what happens at 10 lux and 100 lux? So at 10 lux, plugging in this equation, I get 2511 ohms. By voltage division, 3.57 volts, and the A to D reading is the voltage over full scale times 1023. So it's that percentage of full scale, 732. At 1000 lux, I get 158 ohms, corresponding to 0.684 volts and 140 on the A to D reading. Now calibration curve fit. I know the A to D reading. I want to know lux. So if the A to D reading is 732, I get 10 lux. If it's 140, I get 1000 lux. Come up with a curve fit. It's actually not linear, but doing an endpoint calibration, I can do a linear curve fit. The slope is change in y over change of x, minus 1.67. To get the offset, plug in a number. Like at 10 lux, I should get, well, at 732, I should get 10 lux. Solve for b. So b in this case is 1, 2, 3, 4. So there's a linear curve fit. Matches the two endpoints. Won't match the middle too well because it's not linear, but at least matches the two endpoints. Problem 3 is C coding. Convert the following flowchart to C code. So the first part kind of goes in sections. I want to make port B input, A and D output, and pick assembler. That's the tris registers. Tris B is FF, sets all pins to input. Tris C and D to 0, sets all pins to output. This one, no points off, but that just changes the default to binary. You need it, otherwise the default is analog. It doesn't quite work. This is a while loop. Forever and ever, do the following. Then for the buttons, I can do that with an if statement. So the first one, if RB2, I'm going to toggle port A, clear port D. Else, if button 1 is pushed, I'll turn on port A, turn on port D. So writing FF sets all the pins so all the lights turn on. Toggling on RB0, I'll toggle port D, turn off port A, and otherwise turn off all the lights. So if I haven't turned on the left turn signal, the right turn signal is turned off, and I'm not braking, the lights turn off. I'll do that for 100 milliseconds, and then check. If the brake is on, leave the lights on for 500 milliseconds, otherwise just pulse them for 100 milliseconds. So if RB1 is not set, I turn off the lights, then wait for 100 milliseconds and repeat. So that's one way to write the C code that matches the flowchart. There's other ways. Fourth one, the subroutine. You can pretty much do anything with an if statement. If I want to pass two variables to a subroutine, controlling the left and the right turn signals, I could use an if statement. If left is 0, 1, or 2, I'll turn on none, 4, and 8 lights. If right is 0, 1, or 2, turn on 0, 1, or 2. And any combination then works. So make left anything you want, right anything you want, as long as it's 0, 1, or 2. I can have both lights turn on, the left light turn on, the right light turn on, whatever. Next comes interrupts. These are probably the hardest part of the course, trying to figure out how to incorporate subroutines that are called by hardware. The first one is a hungry, hungry hippo, similar to the third test, but instead of counting every first, third, or fifth interrupt, I want to count 90% or 100%, 90%, 80% of the interrupts. There's a couple ways to do that. One way is to generate a random number. One way to generate random numbers with a microprocessor is to use the time. I'll have timer 0 running in the background, and the time that I hit the button generates my random number. So the first button, player A, counts every edge. I don't have to do anything. For player B, I'll take the time that the button was pushed, mod 100. If it's 10 or more, I'll increment. 90% chance I'll increment, otherwise I don't increment it. So 90% chance I'm going to count that button push. For player C, I'll count 80% of the button pushes. So take the time, mod 100. If it's 20 or higher, 80% chance I'll count, otherwise I don't count. And timer 0 doesn't really do anything, it just counts clocks, and I use that for my random number generator. That's one way to do it. Another way is to set up a counter. Every time I interrupt, I'm going to count mod 10. For 9 counts, I increment. Every 10th count, I don't count. For player C, I'll count 80% of the pulses, or 1/5 of the time I don't count, 4/5 of the time I do count. This isn't quite as good because you can tell that I'm missing every 10th count, every 5th count. It's better to do it random. That's harder to detect. But either way meets the requirements for the homework set, for the test. The last problem is I want to use interrupts to vary the brightness of your taillights. I'm going to have two variables called left and right. These have to be global variables. The left controls the brightness on port A, right controls the brightness on port D. So a couple ways of doing that. One way is to use a single interrupt. In this case, I'm going to call it every 0.1 milliseconds, kind of arbitrary. So timer 0 is being called every 1,000 clocks. I am then going to count mod 100 for X counts. I'll turn on the lights, otherwise I'll turn it off where X is left. Likewise for the right. So if left is equal to 30, for 30 counts I turn on port A, the rest of the time I turn it off. If right is equal to 70, for 70 counts I turn on port D, otherwise turn it off. So this is one way to do it. Another way, if you want to get fancy, this one, the problem with it is this is every 0.1 milliseconds. The lights are blinking 100 times slower than that. So the period would be 10 milliseconds, on or off. So 10 millisecond period, 100 hertz. A way to do that at 1000 hertz update rate is I'll have timer 0 called every 1 millisecond. That's what this does. If the lights are supposed to be on, meaning they're bigger than 0, I'll turn on port A and turn on port D. So light turns on at timer 0. And then n clocks in the future, I set up a timer 1 interrupt, where n is left times 10,000. That many clocks in the future, I then turn off port A, and then I repeat. So this distance right here is 10,000 clocks. And this distance is your left 0 to 100 times 100. So if left is 100, I'm right here. If left is 0, I'm right here. And the caveats, at 0, I can't interrupt in 0 clocks. So if it's 0, I just don't turn on the lights. I can't interrupt in 0 clocks. If it's 100, I just don't turn them off. Otherwise, at 1%, I've got 100 clocks between when I set it and when I clear it. That's barely enough time to call the first interrupt, exit, get back in, call the second interrupt, turn it off. So this will barely work at 100 clocks. It'd be a little bit better if I made this like 200. So rather than times 100, made it times 200. But that's the second way to do it. So that is the final exam for ECE 376 for fall 2023.